Power management is critical for modern ICs. To optimize power consumption, the Unified Power Format (UPF) precisely defines power intent. As a TCL-based industry standard, UPF is essential for complex SOCs and advanced process nodes. UPF empowers efficient and power-aware chip design. Let's explore its significance. To start with some background. So we talk about design intent and verification intent. We also talk about power intent and performance intent. They're related. Power and performance are related. Design verification goes in hand in hand. Okay. In the same lines, we also talk about power intent and power management techniques. So power intent basically, defines the goals. Whereas a power management technique, they're the tools or techniques to achieve these goals. Power is a critical factor in SOC. It's a rate of electrical energy consumed by the chip during its operation. It is a multifaceted aspect, that can encompasses, several key factors like dynamic power, you know, uh, static power, short circuit power. These are gate level, right? At some system level or IP level, we can combine that with activity factor to come up with the actual energy consumed. Okay. What is the importance? Okay. So performance, excessive power consumption can lead to overheating, and this degrade performance or even cause failures. For portable devices, power efficiency directly impacts the battery life, a crucial factor for user interface. Power-hungry chips can require complex cooling systems, increasing the manufacturing costs. High power dissipation can accelerate aging and wear, reducing the chip's lifespan. Efficient power consumption contributes to reducing the overall energy consumption of electronic devices. So it is having an environmental impact also. Let's get into list some power management techniques. Okay. So there's a couple of power management techniques that are employed to address these challenges. Voltage scaling, clock gating, power gating, dynamic voltage and frequency scaling. Okay. Effective power management is crucial for designing high performance, energy efficient and reliable SOCs. UPF, the collateral, is a requirement or widely used to enable power aware design and low power design for SOCs, right? Let's see the difference between them. Uh, Traditionally, low power design has been our focus. Okay, it means you want to save the power and come up with the techniques to do it. Sometime, reducing the power consumption would have affected the performance as well. Okay, the many a times that's one point. Many a times, right? There is no need for you to keep burning more and more power to improve the speed of performance, right? At some point, okay, you can achieve the best performance even at a lower, burning the lower power also. So finding that balance point, having maximum performance at a lower power, right? That's what is about power aware design. Okay, so low power design mainly happens at circuit level, whereas power aware design happens at system level, but also across the stages of design. Okay, um, voltage scaling, clock gating, power optimization, they are some of the techniques in low power design. Whereas power hour design involves power estimation, modeling, power management, thermal management. Okay. So typically low power design happens, in the early stages of design to reduce the power. Whereas power hour design happens through the design cycle to manage the power efficiently. So it means UPF is very, very critical for power hour design. And let's get more details about UPF. So we power to manage the power, we have to capture the power intent, right? So traditionally, this intent was you know, before the days we standardized the things, right? So these were captured in proprietary formats, maybe tool specific. Okay, and the designers would have built the custom scripts. Okay, uh, and there are some couple of other methods also used, like the Verilog or VHDL, that they are used to capture this, the power intent. Okay, some of the power intent is also as was part of the other design constraints. Okay, and sometimes people used to capture them in manual, like used to document manually, and does the power management, right? So this capturing the power intent to manage the power. Okay, so it was the days of non-standardization days. Okay, it has got its own limitations. Okay, flexibility wise, scope wise, interoperability wise, uh, precision wise. Okay, um, all those things. So then comes the age of standardization, and we started with low pass, as low power format. Okay, so low power design techniques, and it focuses low power design techniques and constraints, and the specific design blocks or models. The scope is, you have a, uh, basic IP or a block or a given small, circuit. You focus on how do you reduce the power. Okay, that's the focus. So this content includes the power intent, the domains, power domains, switches, isolation cells, techniques like power gating and retention. Whereas UPF is one more matured version, I can say that, we can say that. So purpose is, comprehensive standard for power intent and constraints. We need to be a little bit more comprehensive, right? Its scope is the entire chip. Okay, the from top level to physical design. That is from the RTL to the physical design. That includes, all the, low power format elements, okay, which are like listed above, and power supply networks, distribution, integrity analysis, okay, etc. So, but to summarize, right, both LPF and UPF both are power management formats, or a formats to capture the power intent. Okay, to enable the proper power management during the design cycle. UPF provides a broader framework for chip level power management, whereas LPF is subset of UPF. See, they are not evolved. UPF is not evolved from LPF, but even then we can conclude that LPF is a subset of UPF. Okay, whereas UPF, many concepts are incorporating from LPF. Okay, UPF unifies power management across the entire design flow. That's the takeaway. So, to summarize, UPF is a standardized way to capture the power intent, and it is widely used across the industry, especially in the advanced nodes and complex SOCs. Let's see some more details on UPF. UPF, Unified Power Format, is an independent TCL language-based collateral text file for specifying power intent, allowing for early power verification, that is before detailed design implementation. So it's a TCL language based. So it captures the power intent. It defines power management. And to minimize power consumptions. It is used along with RTL design. For example, system Verilog files. Okay. It's also used for during verifications, like simulation, emulation, static or formal verification. Okay. And it's used along with implementation too, like for example we do power aware synthesis. So the power aware design, it's also used along with DFT, PNR, place and route, etc. In summary, UPF file are a collateral used along with the VLSI design flow, that is during the RTL design, during RTL verification, during synthesis, during PNR, and then during DFT. So, I mean, the goal is to design keeping power in mind, being aware of the power and going for design. So let's see how it evolved. Okay, it all started, this standard or format started along with Accelera UPF 1.0. It was the initial version that laid the foundation for power intent specification. So next evolution is it became a IEEE standard. Okay, with UPF 2.0. So after that, it came on seeing continuous refinements and it went to 2.1, 3.0, and 3.1, right? The latest version being IEEE 1801 2018. Okay, was UPF 3.1. So UPF's evolution, this evolution aligns with IC complexity, providing standardized power intent and enabling sophisticated power management techniques. See, the IC complexity evolved, improved. I mean, IC complexity increased over a period. So accordingly, UPF also evolved. Okay, providing standardized power intent and enabling sophisticated power management techniques. Let's understand where all UPF fits into the basic design flow. Okay, we know that, right? So uh, after the specifications are finalized, architecture microarchitectures are properly documented, we go for RTL design. Okay, so then once RTL design is done, we go for RTL verification. Okay, design verification, DV. Okay, once everything is good there, we go for synthesis. It means converting RTL into a gate level netlist. So along with the synthesis, we go for logical equivalence check, and sometimes we go for gate level simulations also. Okay, so then once everything is good here, we go for here this verification, we go for PNR. Okay, so then once PNR, the physical design is done, along with physical design we go for timing analysis as well as the physical verification and some other checks. Okay, and these are the things and the stages, right? Now let's understand where all our UPF is say used, collateral is used. Okay, first, power intent definition. Okay, to begin with, you define the power intent. What you do here is you identify the power domains. For example, different voltage levels, power supply networks. For example, pad may be working at some different supply. Unlock circuits could be working at a different supply voltage. And core logic, digital logic circuit, right? Logic circuits could be working. Standard cells are working at different supply voltages, right? Identify the power domains. Then specify the power states, determine different operating modes. For example, architecture level or system level, active, sleep, retention, power domains. You define power switches also. Okay, how power domains are controlled and switched. Sometimes you want to operate at lesser supply voltage. Yeah, how they are controlled, power domains. Identify power gateable elements. Sometimes you want to go for a power gating or clock gating, etc., etc., right? Gateable elements, like which logic elements can be powered down. Okay, at power intent definition we capture multiple other things similar to this. After that, okay, now you capture them and put in a TCL, tickle syntax. Now you create a file, text file, and capture those power intent in a tickle language, tickle syntax. Okay, and we call this as a UPF file. UPF file, okay, um, and power intent is defined here. Okay, we have created the file now. Next is start using it. Okay, at different levels of VLSI design flow. The first where you use is naturally this one, RTL design flow. Here you use. Here. Along with RTL design, use a UPF and you make sure that you are writing RTL design keeping power in mind. Okay, this mainly comes at architecture level. Okay. Okay, RTL design is done, RTL verification is done. What next is synthesis, right? Now, instead of randomly just synthesizing it, do the power aware synthesis. Keep the power in mind. With synthesize the synthesize your design, keeping power in mind. Okay, synthesizes tool uses UPF to optimize the design for low power. Then it also involves, you can also involve in tools insert isolation cells, level shifters, and other power management cells based on the UPF, because you want to save the power, and you want to, okay, power management cells are inserted here. Okay, synthesis portion is done. What next? And the physical design. Okay, it's again is a power aware physical design called as. Okay, what it happens is UPF guides the creation of power distribution network considering power domains and voltage levels. And power aware placement algorithms consider UPF to optimize the power distributions and flow plan and placements. Okay, and power integrity levels, analysis. The UPF is used to verify power supply integrity and identify potential issues. So we know how UPF is used in physical design and why. Okay, next, once physical design is done, you have to verify it. Okay, typically verification here either timing verification, timing static timing analysis, or it's also physical verification, and multiple others also we do. Okay, let's see how UPF is used here, right? UPF, consistency check. Verify the consistency of the UPF with the design. Okay. Okay. And it, here power aware simulation. You simulate the design with UPF to assess the power consumption and performance. Okay. It's basically we are talking about post synthesis simulations. Okay. So, and we also do, static timing analysis, right? Generally, we close, we complete the PD only after is timing closure, static timing analysis, right? Now, in this new flow, you keep UPF in mind, you keep power intent in mind, and close the physical design. Okay, consider power related constraints from the UPF for timing analysis and physical design. Finally, sign off. See, you generate power reports based on the UPF and design, and ensure the final design meets power targets and specifications. If all good, sign it. We got an insight about where all UPF file is used in a VLSI design flow. Let's understand different kinds of UPF formats. Okay, there are two complementary approaches: constant UPF and configuration UPF, to manage power intent within the unified power format. Okay, so we have a constant UPF and we have a configuration UPF. Let's look into this constant UPF. So the focus of constant UPF is it is generic in nature and it is for a given IP or a module. Okay, so defines generic power management constant for an IP or a module. Whereas configuration IP, right, it is not generic, it is specific. Okay, so we cannot reuse the configuration, whereas constant UPF we can reuse. Okay, so configuration UPF maps the generic constraints from the constant UPF to a system level implementation. Okay, so they're complementary. Okay, so now what is next? What is the content of this constant UPF? Is power domain definitions, power states, isolation cells requirements, and retention requirements, power switches, etc. Whereas the content of the configuration UPF is, instance level power domains, power state definitions, transitions, power switch connections, specific power management strategies for a system. Basically, we are talking about system level, way. In the left side, constant UPF, we are talking about the IP level or module level. And what is the purpose here, right? So the purpose of constant UPF left side is to provide a reusable and standardized power intent for specification for an IP. It means constant UPFs are reusable. I can use the same thing for NAND NAR. If nobody writes it for NAND NAR, okay, I'm just taking an example for multiple IPs. Okay, reusable. Okay, so whereas the configuration UPF is adapt the IP's power behavior. It's I'm talking about adapt the IP's power behavior to the system level requirements. Okay, so now you constant UPF is typically created by the IP provider. The IP provider, maybe you are a IP designer, you create it. Whereas integration typically configuration UPF is typically created by the system integrator. Like all the individual blocks are integrated and done the final simulations integration, right? Those guys will do it. configuration UPF. Now that we know there are two kinds of UPF files. One is constraint UPF, other one is configuration UPF. Let's see where they are used and what stages of IC design they are used. Okay. Uh, we can see generally we start with micro architectures, right? We do the RTL coding for a micro architecture. So entire architecture is subdivided into micro architectures. We start RTL coding at a micro architecture level. Let's call them as a modules or the blocks. Okay. So during the, let's call this as the IP itself. Okay. During this IP creation or a module level, we generally use the constraint UPF. Okay. So what it does? Okay, the constant UPF defines generic power behavior. For example, power domains, power states, gating, isolation cells, switches, etc. Okay, as a next stage to power, this microarchitecture RTL design is done, you verified, then you have to integrate everything, configure everything, right? So different microarchitectures they talk to each other, right? And okay, as if they're all part of the architecture, right? So then at this level, our IP configuration level, we use configuration UPF, and it is created for mapping IP to system level requirements. So what it contains is power domain mapping. For example, each module can be working at different supply voltage. So there should be a power domain mapping should be required, and state transitions, switch connections, etc. defined in configuration IPOPF. So once we are done with architecture level, simulation and verification, we generally go for implementation. Implementation generally it's synthesis and PD. They are called implement, actually real physical implementations, right? So we use both the UPFs, okay, together, okay, in this level. So and we both UPFs are used, okay, for power aware synthesis and physical design, power aware physical design and power aware synthesis, and this is for optimal power efficiency. Now let's look into the UPF file structure for inverter or NAND or NOT. Remember, nobody writes UPF file for inverter, NAND or NOT. Nobody writes it. So simple. And many of the features which power intent are not suitable here. For example, power gating, supply domain mapping. They're all not really required for inverter, right? Because single supply voltage and no power down options here. Okay, but then even then I'm taking the structure. Okay, so we have a header here, we have supply power supply definitions here, we have a power domain here, we have a power and ground nets here, and whatnot. So same thing can be, see, these are reusable. Constant UPF is reusable, right? We can do it similar structure as it is can be reused for most of the similar gates, right? uh, Now it's time to summarize and conclude. UPF is a standard format for specifying power intent in ICs. It's a IEEE standard also. Power intent defines power management goals, domain, state, switches, gating, etc. UPF structure includes header, power supply definitions, power domains, power states, power switches, power gating, and constraints. UPF flow involves power intent definition, UPF creation, and then using them along with synthesis, physical design, verification, and sign off. Constraint UPF defines generic power behavior for an IP. Configuration UPF adapts IP power behavior to the system. At implementation level, both UPFs, implementation in the sense synthesis and PD, okay, both UPFs are combined and used for power aware designs. Unlock circuits pose challenges for UPF, but we are using them. UPF benefits include improved, power optimization, design efficiency, and IP reuse. Thank you very much for your time.